Following is a video basically answering this inquiry problem where it says complete the following table. And it says A, B, M, and N are constants. So we have A, B, M, and N right here. And basically what these constants are doing, like you have an M here and an N here. So these are both coefficients for this x to the A, and then this N is the coefficient for x to the B, and then A and B. So these constants A and B are the exponents here, and then we have a +1 and a -1, and you're having this limit right here. We have to complete this following table, so we have to fill this in right here. It says find each limit, so we're finding all of these right here based on these constants here. Now the main thing that you're going to try to find here is, as you see from part A, it says what rule can be made regarding rational functions and their degree. So that's basically what we're going to try to find here, is some kind of trend where if A was greater than B, if A was greater than B, if A was greater than B, then flipping that around, B is greater than A, again 2 other times, and then if A and B are equal. Okay, if you notice M and N, they're equal sometimes and sometimes they're not. We're going to notice that as well, hopefully, in the trends. I'm going to try to show you this in 3 different representations. So I'm going to show you it algebraically. So I'll do the algebraic one on this screen. So I'm going to solve these algebraically here. And then I'm going to use the Desmos calculator to show you not only a table so I can do it numerically here, but I'm also going to be using this graph so you can actually do it graphically as well to find these limits. So let's do this first one here. It says that A is 2, B is 1, M is 1, and N is 1 for this. So algebraically, this is kind of what it would look like. Okay, so we're going to have basically something like the limit as x is going to infinity. Well, M is 1 here, so then x is going to be squared because A is 2. It says right here, A is 2. Okay, plus 1 all over. Now it's nx, n is 1. So it's just going to be x to the b. B is 1, so we're just going to keep that x there. You can just put a 1 there, it doesn't actually matter. -1. So we're trying to figure out this limit right here. Now the cool thing about finding limits with infinity is it makes some of the math a little bit easier. For example, if I try to do direct substitution here, if I just tried to directly plug this infinity in here, I'd have infinity squared plus 1. Okay, well, infinity squared plus 1 is still infinity, and basically what you want to see here, now it's a different kind of infinity because it's an infinity squared, so it's a bigger infinity, but the main thing you have to see here is this 1, this constant, is meaningless. We do not actually need this constant, so it's actually similar to the problem before this. So it's infinity squared plus 1, that 1 becomes infinitesimally more meaningless as you go closer and closer to infinity, so I'm going to get rid of that. Okay, this right here, x is going to infinity, x to the first minus 1, again, x is going to infinity, so you have infinity minus 1, that infinity minus 1 is still infinity, so I'm going to get rid of that constant. So here we have x squared over x to the first. Okay, well this can actually just cancel out, so the x's are going to cancel here. So you end up with just the limit of x as x goes to infinity, and your answer here would be infinity. Okay, so I'm going to put that right in here, so the answer is infinity. But let's actually see this, besides just doing it algebraically like this, let's do it with graph and numerically as well. So A is 2, B is 1, M is 1, N is 1. Okay, it's just following this table right here for those values. Okay, now from here, if you look at the graph, we're going to infinity, so we're going forever to the right. If you notice, this graph for going forever to the right is just raising forever. And if you zoom out, you can kind of see more and more that it's just going forever to infinity. So that actually matches what we have for our algebraic infinity. So graphically, it also shows infinity. Let's use the table. Okay, now since x is going to infinity, that means that you're getting infinitesimally bigger and bigger. So what I'm going to do for the values is I'm going to start with, like, I don't know, 1, and then get bigger, 10, 100, 1,000, and then I'm just going to do a really, really big number. Okay, if you notice the trend here for what the limit is going to, this would be the y value right here. It's undefined at 1, then it goes 11.222, 101, and some change, 1001. If you notice, it's getting bigger and bigger and bigger. So if you do this numerically, it's also going to infinity. So that kind of checks out algebraically, graphically, and then numerically as well. Okay, let's do the next one. This time, A is going to be 3. So instead of A being 2, it's going to be 3. So I'm going to rewrite this really quick. So you end up with the limit as x is going to infinity of x to the third plus 1 over x to the first minus 1. Okay, again, this 1 and this 1 are meaningless. So you have x to the third over x. Okay, so this becomes squared, and this just cancels out. So you have the limit of x squared as x goes to infinity. So it would just be infinity squared, which is infinity. So if you do this algebraically, once again, we get infinity. The only thing that changes here is that this A is now 3. So now when I go to this graph right here, I'm just going to change this A to 3. Okay, if you notice now as x gets bigger and bigger and bigger, it's going steeper and steeper, but it's still going to infinity. You can see if you zoom out, it's continually going up and up and up based on this graph. So based on graphically, This limit would be infinity as well, which matches what we had algebraically. And then if we look at the table here, I'm just going to keep these x values in because we're going to infinity. If you notice, this is also getting bigger and bigger and bigger each time. So it also checks out numerically that we're going to infinity. Now for the third one, what you're going to notice is that your a value is 4 and your n value is 2. So now we actually change the n value here. So we're going to actually, let's just write this one out. So we have the limit as x goes to infinity of x to the 4th plus 1 over x to the 1st minus 1, but that n is 2 this time, so I'm going to put a little 2 in front of it like that. Okay, once again, this 1 is meaningless, that minus 1 is meaningless, because if you just plug this directly in, you're going to have infinity on the top, infinity on the bottom, so infinity plus 1, it's not going to matter. This x to the 4th is going to cancel out with this x right here, and you have x to the 3rd over 2. Well, x is going to infinity, so this divided by 2 is kind of meaningless. You're going to have infinity cubed over 2, which is still infinity. So basically, long story short, this constant right here, when it's a coefficient, this n, even if it was an m, we're going to show this in the next one, it's meaningless compared to the powers. The powers that, since one is bigger than the other, these coefficients become pretty meaningless. The only time the coefficients actually become meaningful is when it's going to be like some of these, but we're not there yet. We'll get to that toward the end of this video. Okay, now let's do this problem with the graph here. So we're going to set a to 1, it's already 1, and we're going to set n to 2. If you notice, it is still going to infinity. If you zoom out on the graph, it's still going to infinity and beyond, as you can see in the graph. Now, if we look at the table right here, x is getting bigger, and our y value is increasingly getting bigger and bigger and bigger. We have 10 to the 8th, 10 to the 20th. You can see that it's going to infinity, so that checks out as well. All three of these check out. So hopefully you can see the trend here for when a is greater than b. When that happens, you're going to always have infinity. Okay, because that power on top is bigger than the power on the bottom. So if x is going to infinity and you have a higher degree on top, that means the top is going to be bigger. If the numerator is bigger, then that's going to beat out the denominator. And since it's a bigger and bigger number up top, it's going to be going to infinity. Now we're going on to a different batch here. Well, this time it's going to be b is greater than a. So it kind of flip-flops the numbers here so we can kind of see what happens. I messed around with the m and the n values as well, so you can kind of see that. All right, so that first one right there, let me write it down really quick. So we have the limit as x goes to infinity, and it's going to be x to the 1st plus 1 over, and this time it's going to be x squared minus 1. Okay, same rule applies with going to infinity algebraically. It's going to be infinity plus 1, which that 1 is just meaningless. Here it's infinity squared minus 1. That's meaningless. Now we can do some math here. We can cross this out with one of these. So you're going to have a 1 up here. So you have 1 over x. Well, 1 over infinity, if you remember from the previous section, that's just going to be 0. Okay, so we end up, if we do this algebraically, we're going to end up with a 0. Okay, let's check this though. So it's going to be 1, 2, 1, 1 for our constants. Let's check this. So 1, 2, this is going to be 2, and then 1 and 1. Okay, if you notice, you have a horizontal asymptote here, which is important. We're going to talk about that in a little bit. But if you zoom out here, you're going to notice it's getting infinitesimally closer to 0, but never actually reaching it. No matter how much you zoom out and go down this line here, it's going to get closer and closer to 0, but never actually reaching it because you're never actually never reaching 0. You're just getting it infinitesimally smaller. And the numerically, this numeric table right here kind of shows that as x is getting bigger, you'll notice that the y, it's 0.111 repeating, then it's 0.01, it's getting smaller, and then it's getting smaller again, and it's even getting really small, 10 to the negative 7th. Okay, now if I added a number in here that's even bigger, you'll notice it just keeps getting smaller and smaller and smaller. Okay, as you go to infinity, and that's what's happening, but it's never actually reaching 0, but it's getting infinitesimally closer to 0. So basically, this 0 checks out right here. Okay, let's check the next one and see if that same rule applies. Okay, so we have b is greater than a. This time it's going to be 1, 3, 1, 1 for the constant. So you're going to have the limit as x goes to infinity of x to the 1st plus 1 over x cubed minus 1. Okay, this cancels, this cancels. Okay, this cancels right here, x over, and then this becomes x squared. 1 over x squared, infinity squared is 1 over infinity. 1 over infinity again is 0. So that kind of checks out. Hopefully you're noticing a trend when b is greater than a compared to when a is greater than b. So we were 1, 3, 1, 1. So we're doing 1, 3, 1, 1. Now if you notice, we're also going to 0. As you can see, it's forming a horizontal asymptote at 0. And if you look at our table here, it's getting smaller and smaller and smaller. Now actually the calculator rounded this off to 0 just because it ran out of number places. So if I get rid of some of these zeros, it might show up. Okay, so I'm just gonna get rid of this one completely so it's not confusing. But as you notice, it's getting smaller and smaller and smaller. It's getting closer and closer to 0. Eventually the calculator rounds, but that's actually not accurate when it said 0 before. Okay, so it's getting closer to 0. The graph and the table both check out this 0. This checks out, so it ends up being the right answer for it. Okay, this next one right here, B is still greater than A, so A is 2, B is 3, M is 2, N is 1. So let's work this one out really quick. So we have the limit as x goes to infinity of x squared plus 1 over x to the third minus 1. Again, these ones are meaningless. Let's get rid of them. X to the third, the x squared is going to cancel here, so you have 2 over x. X is going to infinity. So again, you have 0. So hopefully, again, you notice the trend. When B is greater than A, you're going to have 0 for each of these. Let's check this out, though. 2, 3, 2, 1. So 2, 3, 2, 1. So as x goes to infinity, y is getting closer to 0. If you look at the graph, if you check the table right here, it's getting closer and closer to 0. The y is as x goes to infinity. So that checks out. Now we're on to when A is equal to B. So this is going to be a little bit more interesting, hopefully, than the ones we've been doing. Not that the ones we were just doing weren't interesting, because they were tons of fun, I'm sure. Okay, this time it's 1, 1, 1, 1. So what I'm going to do is write that down over here. So you end up having the limit as x goes to infinity, and it's going to be x to the first plus 1, and then x to the first minus 1. Okay. We're going to infinity, so it's infinity plus 1. That 1's meaningless. Minus 1, that's meaningless. And you end up having x over x. That cancels to be 1 over 1. The limit of 1 as x goes to infinity is going to be 1. Put a 1 in there. So we have something a little bit different than the infinity and the 0. Now we have 1. And hopefully you notice the trend by the time we're done with all this. Let's check with the with this right here. We're going to make these all 1. So we got 1, 1, 1. Okay, and if you notice, it's getting closer and closer to 1 here. As you can see right here, you zoomed out a bunch, it's just getting closer and closer to this 1 right here. 1, 2, 3, 4, 5. So this is 1. It's getting closer and closer to 1. If you look at your table right here, as x goes to infinity, this y is clearly getting closer and closer to 1, as you can tell. So basically, the horizontal asymptote as x is going to infinity right here would be 1, because that's basically what this horizontal asymptote is showing. So as x goes to infinity, you have a horizontal asymptote at 1. And I can actually graph this out just to kind of make more sense. If I just wrote y equals 1, you can kind of see it's graphed right here. It's getting infinitesimally closer to that y equals 1, but never actually reaching it. And that's basically our definition of a horizontal asymptote. Okay, so that checks out with the 1, both with the table numerically and with the graph. Okay, now we're going to do 2, 2, 2, 1. Okay, so for the next one, it's A, B, M, and N are 2, 2, 2, 1. So we have the limit as x goes to infinity of, so it's going to be x squared x squared plus 1, but our M is 2, so I'm going to put a 2 in front of here. And then right here, it's going to be x squared minus 1, and the N is 1, so it ends up being something like this. Okay, now this 1 right here is meaningless because it's 2 times infinity squared is infinity, plus 1, that 1 is meaningless. And infinity squared minus 1, that's meaningless, so those are gone. Constants are always going to be gone like that. Okay, now we have x squared over x squared. That cancels, and you have the limit of 2 as x goes to infinity. That would just be 2. Okay, so numerically we have 2. Let's see if this checks out. Graphically, we have 2, 2, 2, 1. So let's do 2, 2, 2, 1. Okay, and we're saying that the horizontal asymptote is at y equals 2. If you notice the graph, it shows that the horizontal asymptote. Now, it looks like these are touching, but if you actually zoomed in, you'd see that they're not. Okay, it's a horizontal asymptote here at 2. As you can see, it's not hitting 2 on either side. We're just focusing on the infinity side for now. So as it gets closer and closer to infinity, it approaches 2 but never reaches it. If you look at this numerically right here, it's 1, 10, 100, 1,000. And then a huge number here, it's getting closer and closer to 2. Eventually it actually rounds it off to 2, but it actually doesn't reach 2. Again, this calculator is just rounding it. Okay, so we're gonna go back here. That 2 checks out, and then last but not least, we have the 3, 3, 1, 3. This one, we're gonna have the limit as x goes to infinity of, so m is 1, so it's gonna be x to the third plus 1 over, now this time n is 3, so it's gonna be 3x to the 3 minus 1. That one's meaningless. That one's meaningless. If you don't understand that by now, then you better ask me some questions, because I just went over it a million times why these constants cancel out. So you have infinity cubed, and then there's a cubed right here. This is going to cancel with this cubed, and you end up with 1 over 3. Okay, so the answer for this one would be 1/3. So we have 3, 3, 1, 3. So we're going to do 3, 3, 1, 3. Okay, and we're going to change this to 1/3 because that's what we got the horizontal asymptote to be. If you notice, it is getting infinitesimally closer to this 1/3, but never actually reaching it as you go to infinity on the graph. If you look at the table right here, it's as x goes to infinity, we're getting infinitesimally closer to 1/3, 0.33 repeating. Okay, so that 1/3 does check out. Now, hopefully you notice a certain trend when a is equal to b. You have this m coefficient right here is 1. This is 1. 1 over 1 gets you that 1. Okay, this time it's 2 over 1. Remember, a and b have to be equal to each other. That's important. 2 over 1, then it ends up being 2. 1 over 3, 1/3. Again, a and b are equal to each other. Another important part is that your x has to be approaching infinity. Okay, if your x is not approaching infinity, these rules that we just went over will not actually work. So part A says, what rule can be made regarding rational functions and their degree? Well, again, just to kind of reiterate, if the power on top is bigger and you're going, x is going to infinity, then you're going to have infinity for your answer. So that's one rule. Okay, the next rule, if b is greater than a, so b is greater than a right here. So if the power on the bottom is bigger, it doesn't even matter if m or n is bigger, you're still going to go to 0. Okay, if the degree on the bottom is bigger and x is going to infinity, you're going to have 0. And then if a is equal to b and x is approaching infinity for the limit, it's going to be whatever the ratio is from the m and the n. So m and n right here, 1, 2 to 1, 2, 1 to 3, 1/3. So if you have any questions about anything in this video, let me know.